line translation. And we can start. So first, I think we can continue with this measurement vector. So measurement vector we call, or we denote it as vector x of t, and it is the collection of this x1 of t up to x capital M of t, and you can see what we will have in this case here, where A is an array steering or response vector, and here we have some assumptions that these signals from source, they have zero mean. Also, our additive noise with zero mean, then it has specially uncorrelated, let's say, specially uncorrelated correlation matrix, I think. Okay, correlation matrix as identity matrix with variance sigma n squared. And this noise is uncorrelated with our source signals. Then we can write everything in this way. X of t is equal to matrix A. It is array steering matrix times signals from sources plus this additive white Gaussian noise. And here we assume, of course, that we have full rank matrix RSS from this equation. And we finished in the last lecture with eigenvalue decomposition. So we started with this case without noise. And what we will have here, we have this representation of a special correlation matrix, RxX. And you can see that we have only the signal subspace. Also, we have this null subspace, but it is just zeros. And now, let's add noise, or let's assume this noiseless case. So we will continue on this part. Lecture number 17. November 1st. And let's start with case B. It is the case with noise. B with noise, which means before, when we write this case A without noise, we show that sigma n squared is equal to 0. And here we show that sigma n squared, so the variance of a noise, is equal, or let's say greater than 0. In this case, we can rewrite special correlation matrix in the following way. So it is matrix RxX, which is equal to A times RSS times A Hermitian plus sigma n squared times identity matrix of size M. Or we can rewrite everything in the following way. So so if you remember, we show Rxx as U times lambda times U Hermitian. Then here we can write that Rxx is equal to U times lambda times U Hermitian, but this one only for noiseless case. And now we need to add this noisy part, sigma squared, and we can, in this case, instead of identity matrix, we can use U times U Hermitian. Because this multiplication is the identity matrix of size M. Then, of course, we can move to the left side U and to the right side U Hermitian, and we will have that Rxx is equal to U, open the bracket here, we have lambda plus sigma squared, but we here first have this matrix, so we need to add matrix, identity matrix of size M, and the last element here U Hermitian. And now you can already see what we'll have in this case inside of the eigenvalue matrix, but we will rewrite everything in detailed way. So like this one. So we represent it with concatenation of the matrices. So first we need to start with matrix U. It is let's say column concatenation. First one, it is U of S. Then here U subscript 0, so it is the null space of U. Then what we'll have instead of matrix lambda here. So first I will show it as the sum of two parts. So first part from first case. Here we have lambda subscript S and three zero matrices. 0, 0, 0. Plus additive white noise with sigma n squared times identity matrix of size M. And the last part, U Hermitian. So it is the concatenation rows. Here we have U subscript S Hermitian, and the second part, U subscript 0 Hermitian. And now I will rewrite everything here only for this middle part with eigenvalues, and we will see what we'll have for these values. This summation of matrices will be the matrix. So first value, it is lambda 1 plus our noise variance, sigma n squared. Then second value, lambda 2 plus sigma n squared. And this goes up to the last signal value. Here we have d sources, so it is lambda d plus sigma n squared. So it is the first part. And here, before we have zeros, but now we'll have sigma n squared, la 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 la, and the last one sigma n squared. Like this one. And of course here and here, all the rest of the elements is zeros, or are zeros. Let's say. Then, based on this matrix of eigenvalues, we can write the following statement. The smallest m minus d eigenvalues, m minus d eigenvalues are equal to sigma n squared. So this part. Overall, we have m rows and m columns, and here we have for signal d rows, and d columns, and here we have m minus d and m minus d. Then we can easily say that we have signal subspace and noise subspace as before. So signal subspace it is the image of U subscript S, and the noise subspace is the image of U0. Let's add blue underline for signal subspace and noise subspace here. And then let me compare what we have for signal subspace and noise subspace for the two cases. So here we can see signal subspace image of U of S, here noise of subspace image of U0. And here is the same thing. So we can say that the signal and noise subspaces are not changed. The signal and noise subspaces are not changed. Then, based on these two cases, we can go further to subspace estimation. And this subspace estimation will be used for the first our algorithm called as music. But before, let's start with this subspace estimation. Subspace estimation. Here I will use 3 underlines for this one. To start this part, we need to write down our assumption that assuming ergodicity of the underlying random processes. In this case, it means that our received measurement vector and the noise they are ergodic processes. Then we can write down the estimate of the special correlation matrix Rxx. Estimate of the special correlation matrix. It is our Rxx, but in this case we are talking about estimate, so we need to show it with head. So Rxx with head is equal to 1 divided by n. So it is ensemble averaging, and here we have the sum of vector x for time t of n, so t subscript n, times the same measurement vector but with Hermitian. So x for t subscript n with Hermitian. And here n, small n, goes from 1 up to capital N. Or we can rewrite this summation thing as multiplication of the matrices. So here 1 divided by n, matrix x times matrix x Hermitian. And of course, with this matrix x here, with matrix x as the column matrix with the columns x of T1, then x of T2 up to x of T capital N. So x of T1 column vector, and the column vector. We think of size m times n. Complex m times n. Then I will put this equation for estimate of a special correlation matrix into a box. And I will highlight with yellow color the left part with arcs with hat, and the right part with 1 divided by n times x Hermitian. So the estimate of a special correlation matrix, arcs is equal to 1 divided by n times x Hermitian. And of course, if we will have infinite number of these measurements, so n goes to infinity, we can say with this lim with respect to n which goes to infinity for Rxx we had. This estimate will go to the let's say true matrix Rxx. And then, of course, we can rewrite the measurement vector with x of t equal to a times s plus n of t using this x. And what we'll have in this case for the measurement equation, measurement vector equation. Instead of the vector, we will have a matrix X. So here matrix X is equal to A times the matrix of sources for time T1, T2 up to Tn. And first I will show it as column matrix. So here first element is S, vector S for T1, then S for T2, up to S for T capital N. So column matrix column matrix and the column matrix here. And in the following way, we need to represent the matrix of the noises. So plus here the matrix of the noise. First one, it is n for time t1, then n of t2 up to noise vector for t subscript capital N. And of course, this one is column, this one is column, and this one is column. This equation we can rewrite using matrices. Then we'll have, let's say, short notation of this equation. X is equal to the multiplication of array steering matrix with signals from sources for these all time snapshots or experiments, let's say. So it is now matrix and plus the matrix of the noise. I will put this short notation equation into the box, and I will use background yellow color. And what about the sizes of these matrices? So before we write that matrix X of size M times N, so what we'll have for matrix A here? So A is complex. And do you have some ideas for the sizes of matrix A if the size of the matrix X is M times N? Any ideas? No?
M times 1 or M times N?
Yes, first one, of course, M, because the left, let's say, no, the number of rows of X is M, yes, but the number of columns is not 1 and is not N. So you need to think about of this matrix S. So it is the signal from our sources. And what is the number of sources in this case? Huh? Yes, with small d. Yes. So M times d. And of course, in this case, we can easily say the sizes of matrix S. Because the number of rows should be equal to the number of columns of A, D. and the number of columns you can see from the X. So it is equal to N. D times capital N. And the noise N with the same sizes as matrix X. M times N. And for this one, we have slides 8, 9, and 10. So let's show here that we have some slides. First, slides from 8 to 10. So let me switch to the slides and then we will continue. Slide number 8. Here you can see the same things for these cases. When we first assume case without noise. And here you can see this nice representation of eigenvalues, yes, in this case. And for case with noise, we will have this additional part, and you can see the same things which we showed before. And here also a special covariation matrix estimate with RxX, which is equal to this ensemble averaging over n, capital N time snapshots. And here we have this signal subspace estimation. You can see here we assume this X T of N, and it is three different. Yes, in this case, okay. Let me explain. So we assume 3 decays. So for each X of T of N, we have 3 different values for X, Y, and Z. And here you can see the general formula which we write down before. And if we look to the signal subspace, which is this A with mu2 and A with mu1, so this one for X and this one for Y, we will have, of course, this plane or subspace. And you can see that each measurements will be some vectors in 3D, but we need to project it to our signal subspace, and we will have some projection of this measurement vector with some errors, of course, in this case. And then let's move to, okay, first I need to switch here, then switch for you. Then we want to show eigenvalue decomposition of the estimate of a special correlation matrix. EVD of RxX we've had. So Rxx we've had is equal to, we can use previous equation, which is u times lambda times u Hermitian. So it is our eigenvalue decomposition, u times lambda times u Hermitian. And to see what we have here inside of this eigenvalue decomposition, I will show you the subspaces. So first one, it is u subscript s here, and u subscript 0. Let me show the sizes of this matrix. So the number of rows is equal to m. Here for signal subspace, the number of columns is d. And for the u subscript 0, it is m minus d times now we will divide this eigenvalue matrix into two different parts. So first one, it's lambda subscript s, and the second part is lambda subscript 0. And this second and third elements, it is 0 matrix and 0 matrix. So here the number of columns d. For lambda subscript 0, m minus d, and the same for number of columns. So this one, number of rows, number of columns d, and m minus d. And the last element, it is u subscript s Hermitian and u subscript 0 Hermitian. They have the same number of columns equal to m, but the number of rows for u subscript s Hermitian is d, and for the second one, it is m minus d. And now, interesting part here, what if we calculate not the estimate of a special correlation matrix, but if we calculate the singular value decomposition of this matrix X, so the measurement matrix. Singular value decomposition of matrix X. So matrix X can be represented using singular value decomposition in the following way. So we multiply U times matrix sigma times matrix V Hermitian. And one more time in the detailed way. Here we have this U of S and U of 0. Instead of eigenvalues, we will have singular values. But first, what we'll have here with the sizes. So the number of columns is equal to m. Number of rows is equal to m. Number of columns is equal to d for u subscript s, and m minus d for u subscript 0. Then here we have sigma subscript s and sigma subscript 0, and the rest of the elements is equal to 0 matrix. Number of columns and number of rows for sigma subscript s is equal to d. And for the sigma subscript 0, it is m minus d and m minus d. And we end all this part with V Hermitian, of course, with this subscript s, and V subscript 0 Hermitian. Overall number of columns is equal to m. Number of rows for V of S Hermitian is d, and V of 0 Hermitian is m minus d. And of course, based on these two equations, we can show the connection between eigenvalue decomposition of this estimate and singular value decomposition of the original measurement vector. Let's continue. Nota bene that Rxx we've had, which is equal to 1 divided by n. So average of x times x Hermitian is equal to this averaging thing. And here, instead of x, we can write singular value decomposition of matrix x. We'll have u times sigma times V Hermitian, this one for x, and for x Hermitian we'll have V times sigma Hermitian times u Hermitian. And this multiplication of the Hermitian of the unitary matrix with itself, it is the identity matrix, but in this case of size n, because we have the sizes of the matrix X as m times n. And then we can write down for eigenvalue matrix, eigenvalues matrix, lambda. This one is equal. First, we write the averaging coefficient, so 1 divided by n. And here we have sigma times sigma transpose. So because values of a sigma is real, so we can write it without conjugation operation. Conjugation operation, sorry. Obvious conjugate. And this one is real of size m times m. So for this part, subspace estimation, we started with estimate of a special correlation matrix, and now we'll continue with signal subspace estimation and noise subspace estimation. So signal subspace estimation. This one is the image of U subscript S, and maybe we will add some little changes for the previous cases with noise case and without noise case to see some differences here. And here the noise subspace estimation will be image of U subscript 0. Here, the main idea between this subspace estimation and the previous part, eigenvalue decomposition of arc sets, the main difference that in the first part with this eigenvalue decomposition, we had, let's say, true subspaces, so pure subspaces in this case, which means it is not the estimate. We talk about these parts as a priori information. We say this one should be of this size and this one of this size. But now when we talk about the subspace estimation, we talk about only the estimation. So sometimes we can estimate it, for example, original D is equal to 8, but we estimate that it is equal to 9 or it is equal to 6, but the true number of sources is equal to 8. And here we need to let's add, I think, for this eigenvalue decomposition of Rxx, previous part or subparagraph, let's try to show U of S and U of 0 as capital 1. So maybe let's add, I will start with without noise case. So here, to show that this is not the estimation, that this one is pure subspaces, I will add these lines on top and in the bottom, in the top and in the bottom. So it is like the capital S, or the same way it is original subspace. So original UFS, it is not the estimate. And for 0, let's maybe add something like this one with small additional line. It is 0, also pure subspace, not the estimation. Yes, it is like the capital one, like S with these lines. Because next I will show you what if we have, for example, infinite number of snapshots, or if our noise will go to 0. We need to see the differences between the original one and the estimation one. So we need to add capital S here, capital S here. Let's say not the capital 0, but capital O here and here. And in the same way for this UFS here, UFS here, lambda UFS. Also, I will change it for pencil one, and the rest in this signal subspace and noise subspace. So capital S, capital O. And in the same way, we can represent all these capital things in the case with noise. So this case with noise, let me move my page. So here, UFS S capital, O capital. Here we have S capital. And in the same way for the Hermitian one. And the last part, signal subspace and noise subspace for the case with noise. So here this pencil thing. UFS and U of 0. And now we can easily go to the special cases. So this one here, this one here. And now you will see the differences between U with this small s and U with capital S. No, estimation with small s, because we need to see the difference between the estimation one and the original one, let's say original one. So here we write special cases. So as I said before, it is only to see the differences between estimation and the original subspaces. So if we assume lim for image of U with this small s, image for U with small s, so without these two lines in the top and in the bottom. And here we assume for this special case that the number of time snapshots goes to infinity. So what we'll have here? First, I need to show this one. So you see, if n goes to infinity, so the number of time snapshots or the number of experiments, we can say, our estimate will go to the original correlation matrix. And in this case, the estimate of the signal subspace with small s will go to the original signal subspace with U with capital S. In this case, we can say that as the number of experiments increases, the estimate of the signal subspace will be better, and maybe it will better fit the original signal subspace. And vice versa, we can say that if we assume this lim for the same image of U with small s, so estimation of a signal subspace, and now we assume what we will have if the noise variance sigma squared goes to 0. You can see that if our noise will be 0, we will have this case without noise, and in this way we will have the original signal subspace. So image of U subscript capital S. So here and here we have capital S, and from the left side here and here we have small s. So this one, true signal subspace. Let's indicate true signal subspace. For two interesting special cases. And in the following way, we can write down the same thing, but for the true noise subspace. The same operation, n goes to infinity. But now here we have image of U subscript small o or small 0, let's say. In this case, our estimate of the noise subspace will go to the true noise subspace with capital O here. And the same thing for the sigma n squared, or the variance of the noise, which goes to 0. Here we have image of u subscript small o. It will go to image of u subscript capital O. And this one is true noise subspace. So I forgot about these differences between estimation and true subspaces. And also we add all these changes in the previous subparagraph only to see the differences when we talk about estimation and when we talk about true subspace. And then I will give you an estimation of the model order D, but we already have, or let's say we already have all these things, but we talk about this thing using pencil. So that was just some question during the lecture. And now, okay, I will leave it here. Maybe like this one. So, estimation of model order D. Estimation of the model order equal to small g. I will use 2 underlines for this part. And then I will show you eigenvalue profile of the estimated special correlation matrix. Eigenvalue profile of RxX with head. And of course, we can get these eigenvalues using singular valuing position of x, and then recalculate singular values into the eigenvalues. So let's show that. Eigenvalues is equal to 1 divided by n. And here we have this singular value squared. And of course, I goes from 1, 2 up to capital M. Because we do not have any information about the number of sources, and we need to estimate this number of sources. So now I will show you some example of an eigenvalue profile for x-axis. For x-axis, we'll have the number of experiments, time snapshots, and for y-axis, the eigenvalue. Something like this one. So it is our lambda I here, and for x-axis, so here I will indicate 1, 2, 3, 4, 5, and 6. So here we have I, 1, 2, 3, 4, 5, and 6. And we assume these values up to 6 because, let's say, m is equal to 6 here for this example. And usually this eigenvalue profile looks like this one. So for first value, we put value somewhere here. So it is first eigenvalue, then second eigenvalue, little bit smaller than first one, then third eigenvalue, smaller than first and second. And here, for the fourth, fifth, and sixth, we have really low eigenvalues, something like this one, and this one. So I gave you this eigenvalue profile before, but as I said, as an answer for a question. But now we will write it in our lectures. And here, based on this eigenvalue profile, you can see that we have some, let's say, cluster of elements here, and cluster of elements here. And based on this gap between them, we can say that the model order in this case is equal to 3. So the estimation of the model order with D with head is equal to 3. And here we can show that this thing approximately equal to sigma n squared. And for estimation of a model order, we can use different algorithms. So first one, we can say it is Akaike criterion, or as abbreviation, it is AIC. I think it is Akaike information criterion. Then MDL, as I remember, it is minimum description length. And these two algorithms work well for large ends, so the number of time snapshots. So work well for large n. Then we have exponential fitting test, so EFT. This one also works for small number of observations. So exponential fitting test. And let's add that work well if n is small. Work well if number of time snapshots is small. And the main idea is given in the name of this algorithm, exponential fitting test. In this algorithm, if I'm not mistaken, they assume the noise as Gaussian noise, and in this case, it will look like exponential thing. And you will see the difference between exponential line of the noise and let's say the part of a signal. So we will have some signal part and then the part of the noise with this exponential exponential decreasing, yes. And of course, large algorithm, large, it is linear regression of global eigenvalues. Of global eigenvalues. So this one can be used for tensors. So, or usually is used for tensors because here you can see we talk about not the eigenvalues, but about the global eigenvalues. So this one for tensors. And I think for now we can end this lecture. We'll have some time break, and then we will continue with music algorithm. I think we will continue after 10 minutes, so 18:30. Если нужно, можем пока проверить, если захотите. Открыть или откройте? Проверить, проверить.
Они просто в чат заходят и просто тихо дальше смотрят.
So, let's start spectral music algorithm. .1 spectral music. Spectral music with capitals. For the name, I will put 3 underlines, and also I will color 4.1 with red color. So this one was introduced by Ralph or Schmidt. Ralph or Schmidt. In 1979. And let's write down what we have inside of this music abbreviation. So music is multiple. So here from this one we have mu, multiple, then signal. From this one we have capital S and I, signal. And the last one, it is classification, C, capital C. Multiple signal classification. So music MU SI and C. Nice short abbreviation. This algorithm is applicable or applicable, I think applicable to an arbitrary and arbitrary array geometry if the array steering vectors A of theta, which is complex of size m, of course we can write down m times 1, are known as function of theta. Are known as function of theta. So which means we have complete knowledge of the array manifold. In this case, let's write complete knowledge of the array manifold with A capital required. So what is this array manifold? So it is the combination of all these array steering vectors, but correctly it is called as array manifold. So array manifold, capital A. Если я не путаю это понятие, на русском это будет что-то типа диаграмма направленности всей вот этой антенны, всех сенсоров по всем углам тета. То есть мы рассматриваем полную диаграмму направленности, получается. Ну, хотя это и есть диаграмма направленности в этом плане. Array manifold is composed of all array steering vectors, A of theta as theta varies over the entire parameter space. For example, we gave these bounds before, I think. This theta goes from minus p, and it is only greater than minus p. And from right-hand side, we have this less or equal to pi. Yes, minus pi and pi. And also this array manifold completely determined. By the sensor directivity patterns so this one is diagram направленности, in this case only of one sensor, and the array geometry. So in this case, based on this one sensor directivity pattern and overall array geometry, we can find array manifold or overall directivity of this array. So the main things here the array geometry, and the patterns of the sensors. The activity patterns. And let's start with the easiest example. We have only azimuth direction of arrival estimation, so it is with theta value. So first example is azimuth only direction of arrival estimation. Then for this example, our array manifold will be one dimensional because we have only one parameter to change. So it is 1D manifold. And if we use let's say mathematical English, in Russian manifold will be, если я не ошибаюсь, множество переводится. Но в данном случае это не сколько вот множество, а именно общая диаграмма направленности. Там есть два понятия в математике: variance and manifold. Variance — это вот что-то из них множество, и что-то вот не могу вспомнить второе. So this 1D manifold for this example with azimuth direction of arrival estimation can be viewed as a rope wearing through complex plane of size m. Да, вот. Manifold — это вот многообразие, не множество, многообразие. Но вот многообразие антенной решетки, оно звучит странно. И коллектор антенной решетки звучит тоже странно. Поэтому вот правильнее это перевести как, ну, мне кажется, на основе диаграммы направленности каждого сенсора и на основе нашего геометрии нашей решетки, это, по сути, общая диаграмма направленности решетки. And in this case, we can show, let's say, some initial point here, and I will show you some example of this rope. So maybe something like this one. And the general vector, this array steering vector. I show it with dotted line. We will call it as A of theta. So it is the general one. And if we assume some theta 0, A of theta 0 we will have this shift of our initial vector to this place. And here, so we write down that we need the rope which wears through this complex plane of size m, but we have here only 2. So we will show it as this space, real space of 2 axes equivalent to our complex plane of size m. But of course, if you have the bigger number of m, for example 3, you need to put this rope through not the plane, but through this 3D space somehow. And it will show you overall this array directivity pattern or array manifold. And then the second one, we can write down an example for azimuth and elevation. Direction of arrival estimation. So it is the second example. Then you can see we have 2 different parameters, theta and phi. So we can say that our manifold will be 2-dimensional. So 2D. Oh, sorry, I started with pencil. 2D manifold. And instead of a rope, for the first example, we will have some sheet in this case. So sheet, but in complex plane, of size m. So it is really hard to show and really hard to imagine all these things in the head. Okay, this part for array manifold. And next, we also have one point here. With the assumption of subspaces, for these subspaces. Here we assume that the mapping from theta to vector A of theta, to vector A of theta is 1-to-1. Is 1-to-1. So it is proper array design. In this case, our signal subspace. Ага. 503? In this case, our signal subspace will be orthogonal to noise subspace. Signal subspace is orthogonal to noise subspace. Or using images, we can say that image of array manifold is orthogonal to the image of the null subspace of matrix U. I will put these two lines into the box. And then we will go to the direction of arrival estimation for spectral music algorithm. So, direction of arrival estimation. I'll put two underlines here. One and two. So we need to find a set of linear independent vectors. A set of linear independent vectors. Independent vectors. A of theta I, theta subscript I, which is of course in this manifold where I goes from 1 to up to the number of sources D, such that so we need to find a set of linear independent vectors such that A theta I Hermitian multiplied with the noise subspace of matrix U is equal to the 0 vector. In this case, it is row vector. Yes. This one is real of size 1 times m minus d, because the size of U subscript 0 is m minus d times d times m minus d. No, not d, m times m minus d. Yes, because this one of size m, and this one m times m minus d. Yes. So I will put, let's say, our goal for this direction of arrival estimation for spectral music algorithm into a box. And you can see that this first algorithm find these estimates using subspaces, and we need to add that this direction of arrival estimation if only an estimate of the noise subspace is available. Of the noise subspace is available. So image of U subscript 0. Based on this goal, let's say the direction of arrival estimates the direction of arrival estimates are the D maxima are the D, so it is number of sources, maxima of the following equation. So we have the spectral power S for the music algorithm, so S subscript music, which depends on theta, and this one is equal to so here we have a fraction. In the numerator we have the 2 norm of a ray steering vector for theta and this 2 norm squared. And in the denominator, we also have 2 norm of A Hermitian, which depends on theta, times the noise subspace of U, and all this part is squared. And let's see what we'll have in this case if we rewrite the 2 norm using the A Hermitian times A. We can call this one as, yes, this one something like spectral power, which depends on theta. Or also we can call it as cost function. So the cost function for music algorithm of theta is equal. So instead of 2 norm squared of A of theta, we write A of theta Hermitian times A of theta. And then below, we will have A Hermitian of theta times noise subspace of U, and then the same part with the Hermitian. So U subscript 0 with Hermitian times A of theta. I will put into the, let's say, yellow box this U0 times U0 Hermitian. And also I will take overall equation into the box. And then note that we can call this the result of this equation as cost function. So it is the cost function. And maybe I will give you the sizes of this U subscript 0. It is complex of size m times m minus d. Next, let's use our knowledge from mathematical background, and we will assume the multiplication of U times U Hermitian. This overall matrix U times with its Hermitian. What we'll have here? First, I will show this U and U Hermitian using subspaces. So U, it is the concatenation of U of S and U of 0. And in the same way, the U Hermitian, it is the concatenation between U of S Hermitian and U of 0 Hermitian. And here you can see we use, I think it is outer product. So we multiply U of S with U of S Hermitian and U of 0 times U of 0 Hermitian. So here U of S Hermitian plus U of 0 times U of 0 Hermitian. And of course, we know that this multiplication of unitary matrices is equal to identity matrix of size M. And then we can rewrite overall equation using not the noise subspace, but the signal subspace. What we'll have in this case. So it is S subscript music of theta is equal. Here the fraction. In the numerator, it is the same A Hermitian times A. So A of theta Hermitian times A of theta. And below in the denominator, we will have, so first it is A Hermitian, which depends on theta. And here we have identity matrix of size M minus the U of S times U of S Hermitian. And we need to end all these things with A of theta. I will also indicate with yellow this part to show the connection between these two equations. So from the one hand, you can find the noise subspace and calculate this cost function based on noise subspace, or you can use the signal subspace, then subtract it from identity matrix, and you will have the same results as before. So it is just two different angles for this problem. And but we will have about these D maxima. Let's show it using one scratch here. For y-axis, we will have this power, spectral power S subscript music, which depends on theta. And for x-axis, we will have theta. So here theta, here is music of theta, like this one. And let's assume the same example with number of sources equal to 3. So D we've had equal to 3. And we will have something like this one, for example. Like this one, and this one. And we call this one, this peak value as for theta 1, this value on theta 2, and this value on theta 3. And which main disadvantages we have for this spectral music algorithm? So you can see that we need to find the subspaces. In this case, search over the parameter space, is computational expensive. Computational or let's use computationally expensive. And of course, this one only for azimuth direction of arrival estimation, but also we can assume 2 or multi-dimensional extensions. So 2 or multi-dimensional extensions are possible. But very expensive. Because in this case, first you need to find the noise or the signal subspace of the tensor, and only after that you need to find the direction of arrival. So I think that's all for spectral music. And then we can go to what we mean when we talk about uniform linear array. So let's write down example. uniform linear array, or ULA, with inter-element spacing, which is denoted as delta, is less or equal to the lambda over 2, where lambda is the length of the wave, or let's say of our interest. And here, inside of this ULA, so uniform linear array, it means that the elements of this array uniformly distributed, or we can say that they have this uniform spaced elements. So uniform spaced antennas with the same complex characteristics. With the same complex characteristics. So we use same sensors and we put they in the same distance between each other. So for this one, we have slide number 11. Slide 11. And then we will continue with this uniform linear array. So let me show you this slide. So this one, uniform linear array. And here we have omnidirectional sensors. And then I will show you also what does it mean omnidirectional using directivity pattern. And here you can see that we have number of sensors equal to m, and the space between them is equal to delta. And you see we have the same delta for x1 between x2, then x2 between x3, and etc. Sorry. First, I need to change switch here. No. Let's go next. In this case, we can write down and array string vector in the following way. So A of theta is equal to first one, we need to write the scalar. So it is A subscript 0 of theta. And then we multiply this one with exponentials. So e to the power of minus j times 2 pi carrier frequency fc times with time delay tau1, which depends on theta. Where with time delay it is how say it before. Let me check. Propagation time across the array. Yes. In the same way, we can show that we have e to the power of minus j 2 pi fc, and here tau2 of theta. So this one for each antenna element or array element. And the last one, it is e to the power of minus j 2 pi fc tau subscript capital M of theta. Of course, we can have different values for this a subscript 0 of theta for each antenna element, but here we talk about uniform linear array. So they should have the same this complex value. And we call this one as complex directivity. Complex directivity pattern of all sensors, of all sensor elements, of all sensor elements. And then I think I will show this complex directivity pattern here, which depends on theta. And of course, to show this one, which is complex, I need to take the absolute value of this complex variable. So, for example, this one, and for example, like this one. Then what else? So here we will have the origin in this point, and for right side we'll have 60 degree, 120, and here, so it is pi, 180. So 60, 120, 180, and for the left side, minus 60, minus 120, minus 180. So the x-axis for theta and y-axis for the absolute value of this complex directivity pattern. So here, absolute value of A subscript 0, which depends on theta. First, I will start with omnidirectional complex directivity pattern. I will show it with brown color. And this one means that for each value of theta, we will have the same value for complex directivity pattern. We need to stop here and here. So from minus 180 up to 180, we have the value equal to 1. And we call the complex directivity pattern as this one as omnidirectional. Omnidirectional pattern. And if we assume some arbitrary pattern, let's say it will looks like, for example, as follows. So I will indicate here the half so here and here. Between minus 60 and 60, we have points 0.5, something like this one, I think, and something like this one. And for the rest of values, this complex pattern goes down. So let's say this way, and the same symmetrical thing here. So, omnidirectional pattern and some arbitrary pattern. And this pattern for each sensor in uniform linear array. Next, we introduce this reference point, which was given, I think, in the first lecture of this high resolution parameter estimation. let's assume that sensor 1 is chosen as the reference point. Is chosen as the reference point. And of course, we can choose different sensors of this array as the reference point. We will have only one changes in these things. So let's first start with this sensor 1, for example. In this case, we can say that sensor 1 will be as the origin of our antenna array. Based on this origin, let's first show the location in the space of these sensors. So for this one, we use vector P as before. And here I will show it only for 2D case, so X and Y. And for the sensor 1, this location of a sensor 1 will be 0 and 0, because we choose it as the reference point. But now let's go to the sensor 2. So P subscript 2. In this case, we will keep, for example, X value. So it is 0. And now we need to put this inter-element spacing between first sensor and second sensor. So it is delta. Then let's go further. First, third sensor. X is 0, but now the space between first and third, it is 2 inter-element spacing. So 2 times delta. And that thing goes up to the last sensor, vector P subscript M, which is equal to, for X, location point, let's say, is equal to 0. And for Y, it is M minus 1 times delta. And now what we have inside of these time propagation things. So tau 1, tau 2, and etc. If you remember, the main equation for tau, so general case with some variable k, this tau depends on theta. So this thing is equal to 1 divided to the divided by the speed of light, so s. And then we multiply it with vector p subscript k transposed, and times vector d, which depends on theta, where d is the direction of propagation. If I'm not mistaken, let me check. D, no. D is the direction of the source. Yes, of the source. Or we can rewrite all these things in the following way: 1 divided by c times k minus 1 times delta times sine of theta, where k goes from 1 to 2 up to number of sensors m, capital M. And of course, you can ask me a question why we have this equality between left part and right part. And let me one more time show what we have inside of this vector d. D of theta, it is the vector of two values. So for the theta, just let's say for two decays, it is only two values, where first value it is cosine of theta, and the second one is the sine of theta. And then you can see if you multiply P1 transposed with this D, you will have this thing. And of course, for the reference point, in this case for sensor 1, we will have 0 in this case, because both elements here 0 for x and y. So let's write down theta 1 of tau 1 of theta is equal to 0. Then tau 2 of theta. So this one is the time, propagation time through the array. So for the first sensor, it is the reference point. This time is equal to 0. For the second sensor, it is equal to delta times sine of theta divided by c. Then for the third sensor, it is 2 times delta times sine of theta divided by c. And this thing goes to the last element here, tau subscript m of theta, which is equal to the biggest propagation time. In this case, it is m minus 1 times delta times sine of theta divided by s. Divided by c, let's say, by c, of course. And I think we can add one short notation here when we write down the location of the sensors in the following way. We mean that our uniform linear array is along the y-axis. I think we have enough time to introduce special frequency, and then I will show you what we have for manifold of omnidirectional arrays and for arbitrary patterns. So special frequency mu. Special frequency mu. I will highlight it with yellow color here. And this special frequency is calculated in the following way. So mu equals to minus 2 pi times fc divided by c. All this thing is multiplied with the inter-element spacing and sine of azimuth angle, theta. Or this thing is equal to minus 2 pi divided by the wavelength of our signal times delta times sine of theta. So it is all because the connection between speed of light, the frequency, and the wavelength. Because here we can show that the wavelength is equal to the speed of our wavelength, let's say, and divided by the frequency of our wavelength, of our wave, of course. And now, based on these taus, tau 1, tau 2, tau 3, up to tau m, we can rewrite our steering vector in the following way, and also using special frequency, of course. A, which depends in this case not from theta but from mu, A of mu, is equal to A subscript 0 of mu times the following vector. So first value, it is e to the power of minus j, tau 1. So tau 1 is equal to 0, and everything in the power of 0 is equal to 1. So here we have 1. Then E, before we have this minus sign, but you can see that mu is also have this minus sign, so we will have only j times mu, so without minus sign here. E to the power of j times mu. Then e to the power of j times 2 mu, etc., up to e to the power of j times m minus 1 times mu. Or, oh no, of course not. This structure of our vector can be represented as van der Monde vector. So what is this? So van der Monde vector. It is the vector with following values. So first one, it is 1. Then second one, it is some value z. Then z in the power of 2, up to z in the power of m minus 1. So you can see in this case, instead of z, we have e to the power of j times mu. And then we need to put just 1, 2, and etc. When we talk about omnidirectional sensors, this part here, a subscript 0, which depends on mu, is equal to 1, as I said before. Omnidirectional sensors. In this case, a subscript 0 of mu is equal to 1. So we will have only this van der Monde structure vector. And I want to end this lecture with the first, the manifold for omnidirectional array, and then for any arbitrary array patterns. So first we need to introduce vector O. Yes, A subscript 0. A subscript 0 of mu. So let's introduce vector O. It is a row vector, and all values of this vector is equal to 1. So 1, 1, 1, and 1. The vector of ones, so it is real vector of size 1 times D. So the number of sources. Then we need to introduce matrix phi. Matrix phi, which has these complex exponentials. So e to the power of j mu1, then e to the power of j mu2 up to e to the power of j mu d. Or we can write this matrix as diagonal matrix with the elements e to the power of ji, where I goes from 1 up to d. So this thing is complex of size d times d. And if we want to show omnidirectional manifold, so I will use A omni. It is equal to so first sensor is our reference point. In this case, we'll have here only this row vector O. Then the second one will be the same vector O, but multiplied with matrix phi. Then row vector O times phi squared, and up to O theta phi in the power of m minus 1. And this matrix is the row matrix. So first one O transpose, then O transpose times phi, then O transpose times phi squared, and the last element O transpose times phi in the power of m minus 1. So this thing for omnidirectional antenna. And now let's introduce for any manifold for any complex directivity pattern, I think, if we call it correctly. And I think I will show it here on the right side. So matrix A is equal to matrix A omnidirectional, and we multiply it with different complex directivity patterns. So here, instead of A0 of mu, or of 1 in this case, if we assume omnidirectional sensors, we will have some A0 for mu1, then A0 for mu2, and up to A0 for mu d. Nope. We will call this diagonal matrix as matrix delta. And if we show manifold of arbitrary antenna array A as multiplication of matrices, we will write down here that we take the manifold for omnidirectional array and multiply with this matrix delta, which contains different complex directivity patterns. And maybe I will show you with pencil what we will have here inside of these multiplications. And we will end with this for today. So first one, it is O transpose times delta, so this one. Then O transpose times delta times phi, etc. O transpose times delta times phi in the power of m minus 1. This one is rho, rho, and rho. And that's all for today. Next lecture, we will continue with 1D harmonic retrieval problem. We will introduce another music algorithm, but for this, not for azimuth angles, but for special frequencies. And I think another 2 algorithms we will also introduce during the next lecture. So that's all for today. Thank you for this work. If you have some questions, of course, you can ask.